What you were saying, Tommy? Hi, hello. Okay, but we will speak with the speaker, with the mic. Yep, I figured out. Yeah.
So I was just about to start the switch.
Yep, yeah. Okay. That's for the presenter, yeah. Okay. Skip. Europe. Okay. So then share, right?
Oh, you need to allow the screen program.
Where do you see that?
Well, you're not seeing your screen record.
Yeah, I didn't click share. That's why.
No, but share is probably going to tell you that yes.
Ah. Okay, you know this before. Okay. Right. Yeah, okay. Let's see.
It's good. Yeah, no, it's not.
So just click this desktop. Yeah. Okay.
I'm not sure what you want to share.
Huh?
Not your presentation.
Yeah, just the whole.
Don't you want to share the presentation?
But if people if they have like videos and stuff, yeah.
So yeah,
yeah. Seems to be all right. Why is that?
Yeah, due to always three. But the start is the is it on it? But then how does it work? Yeah.
Test, test. Test, 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 test. Working? Can you hear me? Nothing? I can, but it worked before, so what's...
What?
Did it change the frequency? Can you hear me? No. Does it do something? Hello? 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 Can you hear me? It was just this.
So maybe just bring up. Ich muss kurz ein Screensharing stoppen, weil
Okay.
dann stecken wir ihn ein.
Okay. Gut. Sonst noch irgendwas?
Nee, sonst fangen wir jetzt gleich an.
Weil sonst ist noch die Möglichkeit, dass wir noch den zweiten HDMI nutzen, oder wollt ihr den nutzen?
Mir Latte. Du kannst auf den zweiten gehen. Das habe ich gepasst und was du Stück.
Ja. We have a second one as well if you want.
What is easier?
Is
It's
it,
easier
is
if
it,
you send here because then you're also on the camera screen.
Yeah.
So if you bring your laptop here, we plug it in.
is it also okay?
Yeah.
You want this one? Just down here. Do you want the presenter as well? Or
It's the least intuitive presenter ever. It's the buttons are assigned wrong, just so you know. Go ahead. Maybe just one.
Yeah, no, I usually don't do anything crazy, so just the button.
perfect.
If it's close.
Okay, let me put this HDMI2 now.
Okay.
It's still my screen, right?
Yes, sir. Yes.
Ah, sorry, it's HTML1. Yeah, my bad, my bad. Ah,
Excellent. Okay. This looks good.
perfect.
Perfect. And it's also nice to see myself, so I know what I'm doing. Why is audio off? Is it empty? Oh, it's muted. Okay.
Yeah, I just muted, so it's not disturbing.
Good.
Ready? Oh, good.
Yeah. So you want to come this side? Or so I know. I know. Great. Yeah. Up, down. Yeah.
Should I
Yeah.
this out? Yeah.
Are you still sharing it?
I'm still not sharing.
Oh
but
no, you should this.
Yeah, but I can just leave from here. I
No,
should,
yeah.
right?
No, share it, please. But otherwise, you don't.
Ah,
it's
okay.
not in the live stream.
Oh, that is true, obviously. That makes more sense.
Excellent. Now. Yeah, the live stream is quite big. Okay. Good. I know. Thanks. Yes. Sure. All right. So with slide today, yes. Let's start. I'm very happy to see you all. This is the first proper final thing. Like we're actually invite a speaker, and we did this room and so on. So we're trying to succeed in the delay and also to a little transfer issue. Which we smash the face of the Roboy, so expensive. This first I wrote it, so anyway, great to go here. I don't want to talk too much. This is really about the work that student team did this semester. And I'm really proud that Luis today with us giving a talk about his work at Munich. Because he did something very important for the future credit presence. Namely, helping us not spill our food, or did I just spill the secret?
Yes.
All right, so let's Luis. Let me give you this.
Very bad at those. Let's see if it works.
Excellent.
Okay.
Perfect. Good.
Can you hear me? Okay. Good. Perfect. So we just need pain inside. So hi everyone, thank you for having me. Thank you for the kind invitation. It's always happy to be around. I think it was not the fun, but last year I saw something. I'm very happy to be here. I'm really looking forward to this. So I'm going to talk a bit about human-robot interaction and how we can get along with robots and robots get along with us. So it's going to be a bit about a little of history of robotics, I guess, connected to a bit of research in my research as well. So yes, about human-robot interaction and collaboration. And just to give an idea, so this is a bit outdated, but basically it's the trend of human-robot interaction that has been growing a lot, exponentially growing for the past 30 years. And this is because hardware changed everything. And now it's changing everything completely different than what I had 20 years ago. So this allows us to get robots closer to people. And this allows us to design controllers that also allow robots that are very close to things. But at the same time, at academia, we are producing quite a lot of research on human-robot interaction, industry, and especially service robotics and all that case, and still very powerful, especially when it comes to engaging humans. And this lack of being comfortable around. So my research goes in how we can address different points of view. So how we can have robots coexisting nicely with humans, how we can have robots doing this collaborative tasks with humans, and how we can have robots doing extreme collaboration, extreme exchange of forces, and really any kind of tasks with humans. So there are multiple ways that we can address that. I was just in a conference in human-robot interaction, and people were talking a lot about trust, acceptance, personalization. It's missing there the core aspects of planning and control, improve my drawing skills, which I'm hoping to improve every day a bit. But for me, it's basically about three main aspects. So the first, and this is going to research robots as well. So it's first getting robots to work despite humans. So how can robots be in the same environment? How can work despite the humans being there? Later on, we're working on how we can get them to work together. Just the basic skills to get them to work together. And finally, it's about understanding and reasoning about the human. And this is the kind of takeaway message that I want hope everyone to have, is that the future of robotics goes in this direction. So the future of robotics goes in the way that team play. So we understand each other and we play well with each other. So how do we do that? So I'm going to talk step by step and a little bit a different spectrum of research, and then we can talk. And if you have any curiosity about any specific aspect, we can go through it later. So starting on your robot, with robot collaboration alone. So we have all these robots working together. And this has been done for a while, but when you have humans around, you have to adapt to them. Well, first, it's just how robots can work together. So this, I'll go very quick because I don't want to spend too much time on math and anything, but you have to model them nicely. So here's basic modeling when you have multiple robots working together. When you go to the human side, you also have to have the same kind of modeling. But the thing is that once you have multiple robots working together, and also in Roboy interaction, you have a very lower capability to move around, interact, have more constraints, and this is natural. So if I'm holding something, I cannot rotate my arm crazily freely. So I have this constraint that I need to consider. And then constraints are not very friendly to robots, and addressing them is mostly it's quite hard. So the first research direction that I went through is how to relax those constraints. And this was looking at how humans do the tasks, how we do the tasks. So for instance, if I'm taking this model, classic robotics, we would say, you have to do this motion perfectly oriented and put it in the place where I want it to place it, where the kind that should be. As a human, you don't think like that. So you think, I have this table, I can put it anywhere. So I have all this flexibility. So how instead of defining one point, you define a region, a set. I can move the ball instead of moving straight, I can tilt it. It's not fluid ball, so I can tilt a little bit and I can move. So how I can embed that information to the robotic system. And then to play around, I was playing basically the adversary of robotics. So this was in the beginning of my PhD. So how robots can hold despite the human trying to break that. So here I was trying to make the robot drop the ball, and the robot is not grasping the ball, it's just making contact points with the ball. And then we presented and asked people to try to do the same. The robot needs to adapt in changing its flexibilities in a way that would still hold the ball disabled. So it's a nice game to play around.
What sensors did you use?
The sensors basically information. So I knew that you should have hold the ball. So basically the distance between the 2 points should be fixed constant. And I could switch between orientation and constraints the way that allow me to move, but it still reduce the constraints. And whenever the human was not trying to disturb, then I would adjust myself. Okay, but no vision, anything, just put it in analytics. So recently I extended that 2 years ago with one of my PhD students, really, including that to planning. So how we can have this robot doing these complex tasks in this very dynamic and elaborated scenarios that carry trays and carry cups around in a safe manner. We did that first in simulation, but then we were interested more in what happens in the real world, what happens if the human is there and just trying to run the robot. And what happens when you have these contact forces. So this was work with Jonathan and me, to mine. So the first thing was trying to understand reasoning about the forces, the direction. So we could reason about the direction of the human forces that is doing the task, and the interaction with the environments that you have while you're doing the task as well. So this allows us to build this framework that you have basically, okay, this is the input of the system, you have a camera, information about obstacles, you have one goal, and you have the focus. So this, and then you embed all this geometric information that I was talking about for strengths, how to relax them, some basic controllers, and you can have this kind of setup that here it's on the left, on the right side. You can see that the humans, when students just trying to disturb the robot while carrying this cup of water. So it has to address, you can keep a little bit, you can play around, but not too much. So how you can switch between these constraints, the way that you can hold them, and if there is, if you're reinforcing, you can still hold them stable. So the robot understands there is a human doing a disturbance force, and just don't try to move again, embed that in the plan. So once the robot starts to think about, you understand that there is someone making forces there. And on the other hand, if there is a surface that you can use to stabilize yourself, explore that. Just make it use that if you're not doing the task properly, just explore that. Because this allows basically have some compliance while you're moving around the table. So exploring that information is always good.
Why is it so slow?
Which one?
This was a 2x and now it is quite slow. Like, what is the limitation?
Mostly on the robotic side. When you have a many systems, usually this version of Kobo, the Kobo is by manual art, they have moves a bit slow, to be honest.
So it's like hardware defined.
Was hardware, also, we're not really looking on making it that much real time. But that's a good question. I don't remember why we decided that. So we have robots now that can work alone, and then moving to a robot that can work with humans. So my first attempt there was obviously my PhD. This was a big group effort. So this was a big project that we were doing. And the idea was to have robots in airplane manufacturing, because it's completely different than car manufacturing. Car manufacturing, you have the car going, the robot fixed. In airplane manufacturing, you don't have robots at all. Because basically, the airplane is fixed and everybody's moving around the airplane. So it's the airplane that you fly is mostly built by humans. It's manually built. It's still manually built. So how we can automatize that just a little bit, just help the human not doing the repetitive tasks. So robots could do some of the tasks, but the idea here was to, whenever they can, to understand that they couldn't finish and ask support for the person. So the person could help them. So this is some sort of interaction that is nice, but how we can get even closer, that was when I finished my PhD, there was one thing that I really wanted to work on, and I moved to the UK to work on that, and that basically doing this complex and forceful interaction with the robot system. So you have first to think if you have this forceful interaction, you have to think about what you're doing. You have to think about what forces are there. So we model the forces, just have a general intuition about what is happening to the system, if you're doing, if you're cutting, understand what the robot can do while you're holding the piece, how it can be stable while it's holding the piece. So we really have to think about it. And then you think about the sequential action. So if you are doing a chair, if you are doing a piece in a working factory, you have all the sequence of forces, and the robot needs to think about them. The naive approach is just to think, okay, let the robot do every single force, think them individually. And then the thing is that if you have collaborative robots, they have limited forces. So you need to adjust your configuration to a given forces. So how we can make it more natural, so we don't always change it. If I'm doing a task, if you are doing a task, this is very relative, this is more, but if you are doing a task, you are not just switching all the time to a stable configuration. So this is kind of like how we do it. We have a reasoning about the forces that we can hold, and we try to reduce the number of times that we are doing these actions of regress, especially because robots can be slow. And whenever the robots are doing regress, the humans usually don't want to interact with the robots, so there's always idle time that it's bad for the interaction, bad for the fluency of the communication between both of them. So the idea here was to minimize the number of regress, to improve the interaction and to allow this kind of regress there without the surface contact. But of course, if you have surface contact, then you can explore it. You can explore this kind of contact that you have. What kind of stabilizing features you have while doing this task. So the first thing is grasp. That's obviously we know how to do it. The second thing is just laying down the table, and that's really good because you are using the surface to stabilize the system. And the last thing is exploring contact points. So if I want to do a force here, and I just hold it here, just make a contact point at this point, then it's my stable. I don't need to grasp. So it allows me to really stabilize the system in a much nicer way. So how the robot can reason about all of those things in real time to do the task in a more natural way with the person. And then you can use that to do different things. Like I was saying, we can do the chair assembly, and And this is always more hard because the vaccine is very lightweight. If you put a piece of wood with a fall, so it has to be mocked up. But you can see the cutting, you can see the forces that it's doing, and you can see that the robot is trying to adjust itself, like this regressing their resolution. But the point is that the point I want to highlight is that while we are doing this task, you can see that the robot operation can work. You can do those tasks together. But in the end, if you look, the robot alone can do it. But the human can adapt. We are very flexible to do anything. So regardless of how the robot poses the task for us, we can do it. But it's not comfortable, it's not safe, it's not realistic. So no one wants to have a coworker that wouldn't do that to you. And then we start thinking about what we can do in these kind of situations, right? And what kind of tasks have been done in robotics and what directions do we wanted to go. So basically that's what we are doing. We are doing a task that was the objective and we are succeeding, but we're not thinking about reasoning, we're not reasoning about the person, we're not thinking about it's comfort for the person, we're not thinking about it's safe, it's a fact, it's a fact. That was the only reasoning that we had. So we moved, how to take that kind of my one part to build a robot that can really reason about humans. So we can really make it humans wanted to be comfortable around robots, and robots to be comfortable around humans. And then it goes to the issue of what I was saying about teamwork, about understanding each other. And we do that naturally. When I'm working with someone, I know the limitations because it's the same robot. I know the limits that you have because it's actually the same robot. So I understand how you work, I understand how teams work. So we have to have that information for us. So how do you do that? We explore different modalities, and you explore different perception systems and everything that is in your surrounding. So the first thing that I tried to do was embedding haptics. So here was mostly about safety. So if you have this robot that's walking around and hits hurt, there is a contact with someone, you gotta understand what kind of contact there is there. So we did a bunch of experiments, more than 1,000 experiments with different controllers that have different reflex features, that's what we call it. So you can have, for instance, the stop, where it's basically the robot stops while it's making contact. You can have the retractions, the active retraction, where we define, okay, what's the direction that you want to retract. Could be the same trajectory, could be going up, any kind of trajectory, very specific trajectory. Then you can have the vector variability, which is basically allowing compliance. So there is a force contract, the force contract pull you up like a spring mass system. Then we experimented those in different surfaces. So basically emulating what would be a contact with a person, like a very soft one, like a belly, or a soft one, soft like a chest, or a very stiff one, like the head. This is small motion just to see how different they are. So it's good. Okay, so the reason about that, how the reason about haptics. This is one example. So here you can see different kind of contacts being done, and the way we define is first think about safety, and then think about how we can get information about this haptic information. So here you can have different kind of contacts. So this is one contact that is in direction of motion, so you're basically asking the robot go faster. If it's against the direction of motion, you're basically has to go slower because there's something here until it stops. So if you give 3 taps, the robot just stops. And here there is a contact that is rated direction, so it's not direct motion, it's not expected, but the robot's carrying something like a container, so we don't want it to disturb. And now if it's not carrying a container, we have this super zero G that the robot is basically directing the position both, and you can move around wherever you want. But if there is the container, then there is disadvantage from the constraints or orientation of the robot not to allow it to tilt. So how we can explore that? We are building a taxonomy of different contacts and storing that information so we can reason about it, so we can make good decisions regarding it. And then the next one was gesture. So it's very close, Michael. So gestures and posture mostly. So posture is something that we do called thinking. If I see your posture, I can kind of tell what kind of actions you are going to do. And depending on the force, depending on the action that you want to have, I can also reason about what posture are good or bad for you to do the tasks. So if you're pushing or pulling, you're doing a force, or if you just wanted to move around, your posture tells a lot. So how we can reason about that and how you can embed that in the robotic system. So this is all about manipulability. The manipulability is the capability to execute the task. And we are very good on reasoning about how we can do the tasks. And we choose usually the best one. So the idea was how we can reason about that and how we can transfer that to the robotic system, which has completely different mathematics than ours. So we did that with some mathematical tools. So people that were working on EEGs and brain computer interfaces, how we map that, and how we can also use computer vision methods to explore it. I won't go into much detail, it's quite a lot of math theory, but it's really cool to see. And we're still doing some experiments online, a nice, cool video about it. So teleoperation was another interface, and here you're not I'll give away a bit, not too bad, hopefully, but how we can transport very complex objects together. So, we're really trying to see, okay, what's the hardest challenge that we can get in teleoperation. And I will first show the solution that we found without teleoperation, how we can transport liquids with it. So this is a robot transporting liquid, fill it up to the maximum, up to the surface rate of the water as fast as the robot allow it to go. This is the work with reading Rafa, but this is mine. And this is the operations setup that allow us to do those things. So here I'm going to show the safety feature that we embed in the operation that allow us to do this kind of motions. So here we are operating the robot with a cell phone, and here we have interface where we manage the interface we're using. Here we're trying actually to drop the app, we couldn't because of features of safety that I'm going to show. So we think about joint safety. It's nice to show how bad it is. So the joint safety, the Cartesian safety. So what kind basically if you cannot keep the table, it's a good thing to have. And then as you get closer, the robot reasons about it and slows down. And this is manipulability that I was talking to, you don't get singularity motions. And you can see there is no contact point. It's basically this marble going around, and you can really have this nice motion while you're doing. And then we ask people to play around, we make a competition on how you could move cups of water, fill with water while dropping it. And then we did that, we have shown that on Irish, the largest robotics conference in the world, and asked 4,000 people to drop the water, operating the robot of a cell phone. We are very nervous, this is the first day, so we're setting up. Luckily, it worked well. We survived. But then the other things right now is kind of hard. So this was before ChatGPT, thank God. But we are trying also to communicate with robots, how we can better interact with robots, how we can shape trajectories, shape behaviors as language. So saying to robot, please slow down because of the accuracy. So slow down, go close. There are reasons about that, and understand reduce loss when it detects the agent that we see. We extended that. We extended that to first trajectory. So there is a glasses. So please get away of the glasses. Don't move the bottle around the glasses. We have that running in real time with the vision system, of course, and we can play around online with the motion, how we can move things and detect it. And we have the embodiment of the system. So different platforms. If you have a drone, or if you have a humanoid, or you have a manipulator, what kind of embodiment you have. So commands, for instance, get closer, get far away, get really far away can be interpreted in different manners. This work with Microsoft, and there's Microsoft, and our from student is there now. It is the model. I'm also not going too much detail, but they didn't have jet yet at the time. We were using Bert at the time, which honestly I wouldn't see that much of a difference. Not from what we are doing right now. Maybe with dialogues. I think they continue to work with dialogues over there. you say that you use ChatGPT but it's good. It's really good. I think it's a good direction to have robotics. You just need to understand how to use it and how you ground it in safety constraints. Because not always you have good feedback depending on the command. So it's good to be grounded. And the final aspect was what I was talking about, the ergonomics and the biomechanics of the posture and extending from the posture to biomechanics. So this is something that we do. We don't know that we do, but you know what force capabilities you have, and that's all embedded in the biomechanics. So you have to go all the way back to understand it. So this goes back to the task that I was showing on how we can have this same task that is really bad for the humans and how we can improve that. So the reason that the fact that I was bad is because the robots that the humans are going to do the task as we tell them to do as robots. So the human is not going to adjust the robot on the fly to do the task all the time. We're just going to adapt because it's quicker, even if it's very bad. So depending on how the robots pose the task for the human, you can understand how the human is going to do the task. And the idea here was to how we can improve that, how to make it more comfortable for the humans. So it's how we can make this interaction more comfortable. And we were thinking about that was the first goal. The goal that I had was how to reduce the muscular strains while doing tasks with robots, so that you can actually improve the quality of living of workers in factories, because that's the main cause of injuries in most countries, work-related injuries, of course, in most countries. So I wanted to have a system that the robot can look at someone, know the task that it's going to do together, reasoning about that. So reasoning about all the possible ways that someone can do that task. And after reasoning about all the possible ways that someone can do that task, reasoning about all the most activity that the human can, someone can do that task, and finally trying to find the best way, the most efficient way to do it. And it's time that if you go to biomechanics, you talk about mechanics, and this is a lot of biomechanics. This is something that we do implicitly. So it's most of the tasks we aim for minimizing energy, we aim to minimize most activity of our body. So when you do that, you're actually trying to build robots, more human-like robots, because this is basically what humans do. So you have all the constraints, you have the accessibility, which is what I showed before. You have the genetic constraints, which is basically the close connection between the human, the robot, the nation, and you have the biomechanical constraints. I'll go very quick on the biomechanical constraints. So basically, this is a map that you have from the forces that you're acting, then you go all the way to the joint spaces, and from the joint spaces, you go to the muscle spaces. And this is the goal, minimizing muscle activity. And this is basically the equation that you have from joint space to muscle activity that you have to satisfy. That is a natural equation that we have. And it goes from body to body, and the forces that are applied. So you embedded all these in the robotic system. And then you find this problem. So you find the grasp of the robot in the shared object, and you find the configuration of the robot that minimizes the human muscular activity in a safe manner and satisfying the biomechanics of the human. So this can be extremely heavy. I'm talking about thinking about all the possible configurations that someone can do us, and then thinking about all the muscular activity that happens when you're thinking about all the possible configurations. So this is really hard to do efficiently. So I took some ideas from robotics that is basically this localized space. So you do this massive offline computation where you take all the different, basically specialize the workspace of a person. And you compute all the muscle activity in different directions of forces. We embedded everything, so it's got this muscle information distribution. I added information about ergonomics because industry manufacturing, they always go ergonomics, so classic economics from 50, I don't know how many years economics have been there. And embedded it together. And for different tasks, you reason about what kind of tasks you want to do together. I did some tests with friends and people from the lab, people that are invited to do this kind of experience, to see if what kind of functions, what kind of actions the humans would do. And it's quite natural. For instance, you can see on the top the figure, the top right figure, this is a force that you expect a large force in the z direction. So basically holding something heavy. And the red one is the space where the voxelized information says this is good, and the blue is bad. So this is just a very trivial example to show that this is good, this is bad, and this is natural. So you don't think about it, but you have to give that to the robot somehow. And then we did, this was the goal, we tried to put that in the robot system. We did some experiments, so I asked people to do two benchmarks, the robot to do two benchmarks and our system. So the benchmarks were basically the random one, which is the robot just thinking about itself, classic robotics, just think about how I can do that task. The other one, we're asking people, okay, how would you like to interact with it? How you would place this board to be cut or drilled in front of you? The robot is complying, you can play around until you decide, I like this way. And the one we decided. So these is kind of the results that just there's a lot of information on the top right is bad, the bottom right is good, it's most comfortable. And this is kind of the result we got. Naturally, the random one is worse. And it's all over the place. The user defines it's okay if you know exactly how to do it. And the comfortable one is usually the best. So you actually get, we managed to get, was more than we expected. We received like 70% of cost-effective reduction with some experience, so EMG experience by mechanics people. And we extended that to different scenarios. So now we are doing tele-rehabilitation, for instance. So classic rehabilitation, we just have telemedicine, we just have the doctor looking at you, so the multimedia interface. And now you can have an uptake interface where the robot and the doctor are exchanging forces remotely. Then you have some work in that direction, and it's a really nice celebration where we can feel the forces of someone on the other side of the world. But you also can embed information from the doctor about the forces, about the muscle activity of the patient. And the fact we have a machine learning that the person detects pain, so facial recognition, detect pains, inform the doctor what's the muscle activity at that moment of pain, and what forces are doing there. So this allows the doctor to have a more informed decision about the teleoperation rehabilitation. So these overall is just to give an idea of how robotics has been from working beside humans, working together with humans, and finally reasoning about humans and getting humans to work together. And just as a take-home message that I wanted to have, and probably pass the time as always, this is kind of interdisciplinarity. This is robotics is all about holistic views. So you have to reason about everything. So whatever you're going to do, you have to reason, understand what you're doing. So if you're interacting with humans, you have to understand humans. And the interaction is only going to be comfortable if we understand each other and it's comfortable for the robot as well. So thank you.
Yeah, like I had to rewatch the live that we're recording this because you were talking about like pretty fast.
Yeah, sorry, I do that. I usually go over time, so I try to go.
What's your absolute favorite like physical experiment?
The leadership position is always really cool. It was a bit surprising. We had the idea on another line that we were working on another thing, and then we started modeling and it was very quick. And the first time we put it to work, we were so afraid to put just a little bit of water and have a colleague that is biomechanics in all of us. Easy see, and then start pouring more water. This much. Start pouring more, this much. And then we wrapped everything and you're sure that it's okay. And it worked for that was really, and it's fine. It's small ways it works really nice. But all experiences, it's nice. Even the experience by mechanics that all the engineers, it's forever to do. It's really But it's really nice to see the results because we learn so much doing experiments. So in the experiments we had one of the participants that never done real life, never done any drilling or cutting. The results of this was I had in the paper I had to write a second just because of this person. And it was so completely off everything. And it has got to everyone to understand why we're so far away from everything that we expect. And then we finally figured out we had to explain. And it's crazy. So it's really nice that no matter how much you think, there's always something to learn.
It's the most fun part of the humanism. Like,
It's fun. It's more nervous as well. Because usually there are a lot of long words together, but it's way more fun.
Yes, I saw you don't have the VR interface where you're still not so. Why coincidence?
Did you like on this build-up? Did you ever look into external perturbations?
Yes, we actually have it somewhere here. So we have running a sort of like index controller where someone can just pull the robot and they will move this motion without it. Further, if someone just jumps in and talk about
Yeah, we can go to program the robot.
so, but it's and it's running well. It's 7 meters, so it has to like most of it.
Like if you think if you put it on the Roboy, like on a grid base, if it's going to drive around, if it's like common things and so on, that you could compensate that.
We are working on that. So we are working on 2 mobile platforms. One is the big mobile based company.
AMR.
It's not,
Auto.
it's a very famous one. Clear path. So it's a clear path with UR10, massive one. And do a pint into like a 1 liter. And then it's very stable. The only thing is that the communication with your body, multi-operator communication with the platform, is around 20, 30 milliseconds, so it's very slow. So you have to compensate, have to put most of the motion to a system that is play around on how much the base can handle it so slow. And we are doing that also with the humanoid mobile version that we have garbage. And that one is it's mounted to be very compliant. So we have basically a magnetic spring, the base like a bar with a spring, and every time it moves, it does this motion. So that's really hard because you also don't have the sense information on the base of the arm to say, okay, this is the motion that it's doing to compensate that. So we are modeling that we are going to choose from. So basically modeling that and use input shaping. Input shaping has been shown really good for compensating these levels, better than expected. And then with that, we can do the experiment. We still don't know the limits, how much we really do the factors. We probably won't be able to fill up to the surface extension because of the uncertainty that we have. But knowing the uncertainty to have a bound for the uncertainty, we can at least know beforehand how much it feels. Yeah.
Okay. Yeah.
That's for that. There's a little setting thing here. There's two presents, please. One from Georgia, but we're drinking the break, so it's and also and you can pick the size, so there is like I hope it's doing fine. If not, it's good for the best.
All right. Perfekt. Okay, das mit dem Stream funktioniert alles?
Gut.
Oder?
Ja.
Sauber. Das funktioniert.
Perfect. So then we're moving over to the student presentations.
It's not. Okay.
Yes. Share your screen.
You need to stop.
Can you unshare yours?
Yeah. Yeah. I still not.
Sharing.
It just says other participant.
You can just exit Zoom. Maybe I can admin exit.
No, let's move this. Oh yeah.
Yeah.
Next slide.
Ah, perfect.
Sorry, does you have a PowerPoint? I think is.
I will. I think I'll fuck that up in a second.
Yes, fair enough. Now it works. Can you see that on the Zoom?
Yep.
Cool. Does that disappear too? That thing here? So, like, okay, so this one is still there, but right. All right. Is it still doing the sound then? Or?
Yeah, I'm trying. So then this has the least intuitive user interface I've ever seen. SAP, yeah, well, that maybe works. That's correct. Down, where's it down? Up now, down. Okay. Okay. Fine.
Should we start? So hi everyone, welcome to the Roboy finals. Is it the wrong way? Okay.
Perfect.
So this is Niels, I'm Marcel. We are the new Tandem Control team, and we'd like to share a little bit of our work that we did this semester. But to get started, we prepared a little video so that we can show you the problem that we were trying to solve. So yeah, enjoy. That's the success dance, exactly. Right. No, I don't want this again. So as you can see in the video, Roboy is currently having problems with imprecise movements, which is why we're giving the semester goal here. So we try to design, train, and deploy a neural network to perform joint space trajectory for Roboy 3.0's arm in hardware. And how we try to achieve this, we just prepared a little timeline for you so that you get a brief understanding of what we did. But don't worry, we go into more detail in a minute. So yeah, we first started with research and planning, just to understand how we could actually solve this problem. And yeah, spoiler alert, things didn't really go as planned. So, but yeah, you will see. We then continued with a mechanical setup of the test bench that we actually brought with us here today. And yeah, after deep diving and doing further research, we came up with the very first algorithm of the two that we'll present here, which is called G2P. And after finishing the software setup of the test environment, we were actually able to implement the very first version of this G2P algorithm. And by doing that, we were also able to record the very first data sets. And since we're so proud after this was working, yeah, we just had to share the little success here. And now this time it's working with Alpha Tiger, I think. Yeah.
Last time the music.
Yeah, we had to sing along. Right. And so using this training data, we were able to train the G2P ANN for the very first time. But we encountered several issues. So we had to do some further research. And after a while, we came up with a second algorithm called the MPC, which Notes will be talking about. And yeah, going from there, we implemented a second version of this G2P algorithm as well. So now we have like two approaches and finished the implementation of this MPC algorithm as well. And so as always with every project, we had to fix the remaining issues towards the end of the semester. And yeah, basically just before this presentation, we were able to deploy our current results to the test bench here, which Niels will continue with now.
So, doesn't matter. Okay.
You don't need this.
All right. Right. So we decided to first build a test bench to test our different control methods that we come up with. And this is, of course, to be able to have fast iterations between different control methods and a safe environments, because some control methods will go haywire in the beginning, and we don't want to damage the actual Roboy. Also, we want some way to have automatic evaluation of how well our control methods performs. So, and this also comes into this fast iterations. Also, we didn't have an experience in ROS. So building this more simple system was a good stepping stone to build up to the more complex Roboy. And so we designed this test bench to, in the beginning, have 3 different actuators. We had the flex, extend, and also we had a dynamic load control. But we didn't have time to implement this load control in the end. So at the moment, the test bench only have flex and extend like the arm, and also has an angle, magnetic angle sensor, so we can perform close loop control of the angle. That is what we want to control. And this is a brief overview of how every subsystem is connected together. We can talk about this later. And here's the software architecture. So the 4 different ROS nodes we have. So we have the bench node that is closest to the hardware. So that it kind of acts like a interface to the hardware, and also sanity checks the input that we send to the hardware. So we don't damage it that easy. And to the bench node, we talk with the controller node, and this is where we run our control methods. And so the different control methods, we can easily just swap out by starting different ROS nodes. And then we have an evaluation node that sends the waypoints to the controller node and then also measures what angle the joint actually did, so we can evaluate how well it performed. And while all this is running, we can run our recorder node that simply dumps the data stream that we collect into a CSV file. And this can be used for evaluation later and training our neural networks. Right, then Marcel will talk more about the algorithm.
Perfect. So yeah, now finally, I will continue with the very first of these algorithms. And yeah, the reason why I included this picture of cute baby Roboy here is actually because the way this algorithm works is very, very similar to the way we humans learn when we are newborns. And so perhaps some of you noticed that when a baby lies on its back, it just like randomly moves around. And when they grow older, they will start to learn particular tasks. So that they start with a general understanding of their capabilities and then build up, for example, with a particular task, which is walking. And so once you understood this like basic biological principle, you basically understood this whole algorithm, because all it does is it tries to implement this into the way tendon-driven robots could be controlled. And so to give you an overview of what I mean by that, we now understand where GTP comes from, because it stands for general to particular. And it actually provides very good results for tendon-driven robot control, which is why we were starting with this algorithm here. Because as you know, we are facing a lot of non-linearities in tendon-driven robot control. So the underlying problem that we are facing here is nonlinear regression. And we solve this with ANN that we feed in kinematics data so that they can output activation to the motors in order to achieve those desired kinematics data. So the goal here is really to create and refine the inverse mapping that I tried to actually show down here in the graphics. So you have the kinematics that you feed in, and because it's very well trained, it will output the motor activations. And so the end result will be this ANN. Right. And so let's start with the very first phase of this algorithm, which is called motor babbling. You can simultaneously watch what it does right there. It generates random motor activations. So it's the equivalent of the baby doing random movements when it lies on its back. And it collects training data. So with those activations that we feed in, we can basically collect the training data, the kinematics data, and by that we can create an inverse mapping. So it learns how to map kinematics to activations. And we actually tried out different implementations of that. So we had deep neural networks, multi-layer perceptron, big multi-layer perceptron, and also recurrent neural networks. But it turned out that the best performing one was actually the multi-layer perceptron. And so if you remember from the introduction, we actually had two versions of this algorithm. So the main reason for that is because we also had two versions of this motor babbling. So we started with the very first one with just one number, a random number generator, and with a normal distribution to choose for those activations. But then we decided to go on with another version, which is now using two random number generators and uses uniform distribution. And so what we did here in the graphics, basically, we used the same neural network, but trained with different training data. So on the left, you can see the one that's trained with the motor babbling version 1, and on the right, you can see the one which is trained with motor babbling version 2, and you can see a slight improvement with the neo version. So that's why we currently add. And so now there's this second phase, which is called the refinement phase. And that's the equivalent of the human starting to learn how to walk. So, and since we only have 1 degree of freedom here, we had to come up with a different solution for that. And so we started with something called point-to-point movement. So basically we would define a set of waypoints that our system is supposed to follow. They don't have to be equidistant, like not in this graphics. You can just basically generate random waypoints. And our goal here is to measure the difference between the waypoint it actually went to and the one it was supposed to go to. And so that gives us a reward. And when we think about reward, it just comes natural that we think about reinforcement learning, which is actually exactly what it is. And the reinforcement learning is rather complex because it's consistent of two policies. So don't worry about that. I will just explain like the general function of this, because if you see the circle here, all the thing that it does, it generates kinematics data that we then feed to our ANN. And by this, we can predict the activations that are required to achieve those kinematics. And so by that, we can interact with the system environment. So in our case, it was following those waypoints. And the reward that we get, so basically the error that we get from this interaction, we can use that to define more training data. And so by going through the circle, we generate more training data that's particular to the task. And by that, we can refine the ANN and hopefully get better predictions. But so since this is still the very first version of this G2P algorithm, and we have it as an open loop implementation, but we built on top of that after realizing we had some problems with that by implementing a closed loop implementation. And we simply added a PI controller before putting in the kinematics data into the ANN. So all we did was taking the joint angle that was output from our system, so put it back into the PI controller as a feedback. And by that, we can then feed in the kinematics to our ANN. And yeah, that's basically how we did it closed loop. And so now Niels will continue with the second algorithm.
All right. We also implemented another approach that is based on model predictive control. And to perform model predictive control, of course, we need a good model of the system. And this we achieve by training a neural network to predict what happens in the very next time step. So we feed in what happened maybe in the last second, and out we want this model to predict the system state. So what angle does the system have? What torque does the system apply on the different biobricks, given the PVM that we have supplied. And here we can see an example of the banding data set. So for example, we simply use our neural network to just predict the very next time step in this time series. And to evaluate this, when we're training the system model, we want to see that it performs well. That it can be able to predict how the system evolves given a certain input. And here we can see that it does predict well how the system evolves. How the system actually evolves is the not dotted line, the continuous line, and what we predicted how the system evolves is the dotted line. And as you can see, the dotted lines follow the continuous lines as well. So we know that we have a good system model. And since we have used our neural network to predict how the system evolves, we now can evolve the system in a differentiable way. So we can use techniques such as gradient descent to adjust the input to make the output, to make how the system evolves the way we want. So we simply evolve the system and put in how the system evolves in a cost function where we define what we mean by it performing well. So for example, we want the angles to follow the trajectory we want, of course. And we want the torque to be as low as possible. So it's kind of like an arm. You don't want your muscles to fight each other, but still you don't want the tendons to become loose, right? Because then they can tangle up. So it's quite a hard control program. It's a lot of factors that need to go well. But since we have a differentiable model of the system, we can optimize input. And this is how one of these optimizations look like. So first, before we have begun to optimize it, we can see that the dotted line doesn't follow the supposed line at all. But
It's still on.
Here's how the system is simulated to evolve now. It just stays at 0. So it just stays constant because we apply 0 PDM. But when we begin to optimize this input from just constant 0, we optimize using gradient descent. And now we can see that the dotted line follows the green line very well. And the red line, which is torque, is close to 1, which is the optimal torque. So it's not too stiff, not too loose. And I'm just showing half the problem here because there are way more variables in the system. So if I would have shown them all, it would be too many things in the diagram. Right, so now I have evolved this in an optimal way. We now have pairs of optimal output. For a given output we want, we now have the optimal inputs. Then we can train another neural network that we feed this output, the waypoints we want the system evolving, and also how the system was in the prior moments. And now this control model is able to predict the optimal inputs. And now we can simply use this to control the system, the actual system. So if I can make it go to new position, for example. And now if I try to disturb it, it will fight back. But as soon as I let it go, it makes the tendons as loose as so it's not necessarily stiff. Okay, I think I was a bit over on time there. But so what is the current status? We built a mechanical test bench. We created a ROS based framework with testing controllers. We finished 2 multi-balancing implementations of the GTP algorithm. We extended the GTP to be closed loop. We implemented 2 refinement phases of the GTP. We trained GTP ANN with new multi-balancing, and we were able to do a whole lot of stuff with the MC system. So, over to Marcel.
1 minute to go. Let's see. So, all good, all good. We're just in time. Right. So yeah, did we reach our goal? Not quite. So we were able to implement a few solutions on our test bench, but there's still something we need to continue with. Yeah. So challenges. Boy, where do we even start? For me personally, I had lots of problems with overthinking and yeah, not trying out many solutions fast. And that's why, yeah, I now know what agile development is and why it's useful. So, Niels, we want to say more?
Yeah, one, I guess, challenge is you're always short on time for this kind of projects, as well as now. Yeah, that's the last thing I want to say.
Yes, some time. Yeah. Yeah, right.
What should we say?
Exactly. Oh wow, that's yeah, irritating. Yeah.
Are you giving up on doing anything with robotics yet?
No, not at all.
So I didn't.
Are you giving up on robotics? Was it so painful that?
No, not at all. Just want to do more.
Yeah, actually, that's what we'll speak about. So yeah, I might continue with this project, but yeah, it's not official yet. So let's see.
Only 6 months, so.
Exactly.
And then you have 1 joint. And you get 2 more.
And then you get 2 drugs and you're super fucking high.
But no, it was actually very fun as a project, and yeah, exactly what I wanted to do. So no, not giving up.
I had a question about roasting.
It's quite a lot of slides. Was it this one?
Yeah. So you have evolution mode and
Yeah.
encoder.
Yeah.
So in encoder mode you report the data and
Yeah.
train a model.
Yeah.
And what was the evolution mode?
So it's the evaluation node. When we start that, we can supply it with a trajectory the controller is supposed to follow. And then it can see, like, then it generates a report that we can see like how the angle actually changed over time compared to how it was supposed to change.
But that trajectory will be generated by national
So that is sent by the bench node. Yeah. So yeah, it should be maybe a arrow from the bench node over to the evaluation node. That is correct. Yep. Yes. Probably the next one. Okay, good job.
Good job, man. We get to that. That's nice. Well done. So you are which one?
Assisted navigation.
Oh, this one here? Right. Okay, let me just quickly close this one. Don't close this, just have this. That's not for you. And if you want to use, you have a presenter, but you can also just use the slides here. And maybe put this back on. This. Is it only you presenting?
Yeah, this is only.
Okay. So yeah,
it's.
Oh.
Test. Okay. Okay. So, hello everyone. My name is Roboy Mahendra. I'm from the assisted navigation team. Unfortunately, one of my teammates is currently sick today, so it's just going to be me today. And maybe I'm going to start off with the semester goal of our project, which are, as you can see, is to integrate 2 time-of-flight sensor into Roboy and then transmit the data onto the operating staff, or at least available in the raw stack, and then prevent the driver from driving into obstacles. Yeah, so we're gonna go with the planning phase right now. So maybe I'm going to explain some of the considerations that is going into this, maybe our planned architecture. So originally we just, we have a time-of-flight camera, right? And then we're gonna have the point cloud data in front of and the back of the Roboy. So, we're gonna make a drive mode that we call propellant field, that is going to slow us down as it gets near an obstacle, and then maybe do a hard stop and basically just before it collides. But then we had a discussion, and then how do we really differentiate between Roboy wanting to really interact with the system, let's say Roboy wanting to push this chair, or Roboy want to move this banner right here, between that and then colliding with an object. So we decide to make like this architecture with multiple driving mode, which are basically manual mode, which is just like the power system, is just the directly outputting the user input onto the motor, and then this steer mode, which is like maybe the most complex drive mode we have that we still doesn't have, which is basically, we're going to use the point cloud, we're going to assume the operator wants to go to a point like a certain distance. You're gonna have the map, so let's say I'm Roboy right now, and then I'm going to have a map of this table right here, or more or less like this part, and then maybe a little bit right here. So what hopefully it's going to do is, it's going to generate a waypoint right here, and then maybe just right there, since we don't know this part right. So it's going to navigate right here, and then after going to the first waypoint, it's going to rotate back to forward and then make another plan. So that's the plan, at least. And then, of course, for the development process, we can't really test it directly onto the Roboy, since, well, if it crashes onto something, it's bad, of course. So we implement like a simple decibel simulation. So as you can see right here, it uses the TF data, and then we make sure the behavior is as expected as the user input and the TF data.
So how is it connected, the time of flight data you have developed and the simulation?
So yeah, it's actually, right now it's not really a perfect simulation. So the time of flight actually I usually just put it onto the table, and then I give the robot, of course, input, and then I usually just try to move an obstacle.
So in simulation, you don't use the option
Yeah.
of simulation, but you use the perception from the real world, and then you have obstacles.
Yes. And then, yeah, this is the validation process. And then I'm going to continue with the challenges we experience. So at the start of the project, it's like maybe, yeah, I didn't ask enough. And then, yeah. So I implemented this whole system with basically the full potential field, the manual, and then the steer already being in the progress of development. Unfortunately, it was unable to be integrated onto the current wheelchair system, and then we basically need to re-implement all of those again on top of the current existing platform. Okay, so that's the first thing, and then at this point, it's already like 3 months into the semester, so time is really tight in this situation. And then another challenge came up. So maybe we can play the video right there. I'm not sure if it's going to be visible right here, but it's kind of maybe in this part right here. But one of the time of flight cameras seemingly gives a random data when the depth it perceives is out of range. So maybe you can see in the video right here. So this is the camera itself. And then this is the data. So this one, it works fine. It gives the correct point cloud. But then if it goes out of range, maybe you can see right here, some points just, until now, I'm still not sure what happened here, but the point just seems to be moving into the, right in front of the camera itself. And then, of course, it's not going to work if it's used either in the steer mode or the repellent field mode. And then the next challenge, believe it or not, happened yesterday. So, okay, one of the time of flight seems to be faulty. It's okay, we're just going to install it in the back and then maybe have a working manual and repellent field in the robotic integrated, and yeah, maybe it's an improvement. But yesterday, I was just changing some parameter, and then it just suddenly didn't give any more data. I tried unplug and plug it. Believe it or not, it doesn't work. And yeah, basically I took it out of robotic and then just trying it. And until this morning, I still don't know what happened, but it's basically still not solved. And then, yeah, unfortunately, when it was working in robotic, I haven't took any footage, so no demo here. And yeah, it's really unfortunate and really frustrating.
But it was working.
It was working from the day I installed it Saturday last week until Tuesday. It was working. I just didn't took any footage of it. That's why it's and yeah, basically nothing. Unfortunately, nothing really tangible to show from for now. And this is just basically the same footage of the simulation show before. And then, yeah, this is also kind of unfortunate, yeah, because since I didn't took any footage, the video itself is Well, not really my project work. But yeah, this is really sorry. Sorry? Yeah. Well, that's basically it from me. And
Questions?
So like, were they dropped or they just died?
No,
nothing.
Just died.
Can you go back to your first challenge?
This one or
The-
yes, this one.
So can you please repeat again what was the issue with the
Okay, maybe.
it's incorrectly formulated, so it's not when out of depth. So like in front of the camera, it shows there is not like an object in the middle.
Yeah.
And then you can't put something in front and it reads properly the object. And then you take the object away and there's exactly
No, it's just
it shows there's something there.
or
It's like a cone. It shows the cone towards.
yeah. So this point right here is basically the camera where my mouse is, and then it's being the value itself. It's kind of being mapped onto like a color, and then the color red is basically really near to the
There's the globe
yeah.
before, it works if you close
Yeah.
it up,
So
if you go away, it doesn't work.
yeah, so this is me in front of the camera, and then after I move out of the camera, all the points seemingly just move toward the camera itself, which is of course not true since there's nothing there. Yeah.
All right. Yes. Open.
Should I choose something here?
The presentation. We need to connect like here. Streaming. Okay. You start?
I'll try again.
You start pressing?
I'll try. No, it doesn't start casting. It is connected to the same account, right?
Yeah. I mean, where we go, maybe just reload.
Oh, no, didn't you have this account?
Otherwise, we can always stop the presentation and we switch over to this one.
Representation. System presence.
Okay. Welcome to our presentation. We are team Immersive Telepresence. Daniel, Dennis, Dan, and Susanna. So, our goal for this semester was to improve the operator's feeling of telepresence during teleoperation. Basically, to make the operator feel like he's really present in the body of Roboy and not like he's playing some old lagging video game. So how we wanted to achieve this? First, visual perception. We added 180-degree cameras, and we do a motion compensation to reduce the delay between the head movements of the operator and the thing that the operator sees in the VR glasses. For the audio perception, we added a new stereo microphones. And the second part of our goal for the semester was to improve the operator with additional contextual information to add some extra information that the operator wouldn't be able to see themselves. Now, okay. Let's watch a video first. Okay, so this is an overview of the system architecture, the communication stack between the robot and the operator. We chose WebRTC for the communication, more on that later. So the data we sent from the robot are, for example, the stereo audio, the stereo 180 image, and we can add some extra data, such as run face detection or face recognition on the robot side and send the extra data to the operator. And from the operator rec, we sent data about the head movement and other control inputs, as well as also the audio from the operator. So the standard use case, how it was before with motion, was that you send an image from the camera on the robot's head. The operator sees this image in their VR glasses, and then if the operator moves their head, then you will send the head movement data back to the robot, then the robot moves their head, and then you have to send the new image back to the operator, and then the operator sees the new position. In our approach, we added a motion compensation, which shortens basically this cycle, so that thanks to the 180 degrees images, we can always show just a part of the image to the operator and react immediately to the movement on the operator side without having to complete the full cycle first. And this should decrease the delay. The system architecture, basically, with the system architecture of the Unity project, we really emphasize that it has independent and easily replaceable or extensible components. So now the components are independent. We can, for example, for the server connection, we can easily replace which communication stack we use. Also, for example, for the input system, we use the VR headset, but we could easily replace it also, for example, with sense glass and so on. And now
I'll continue. Okay, so since it's teleoperation project, we want to control the robot, and so basically robots motors, and we need ROS for this, and we use particularly ROS2. Since Roboy uses ROS1 nodes for all the motors and sensors, we use the ROS bridge. And our node is subscribing to the head orientation sensors and publishing the joint movement positions and wheelchair control as well. For the improving the sound perception, we add stereo microphones that are located in ears, right one and left one, obviously. Also, we use the pulse audio for sound amplification, for the noise and echo reduction to make the sound. Visual vision perception is improved, as Susanna said, with the 180 lenses that allows to see more. So basically, you can see the output of those of cameras with those lenses. We use OpenCV to recenter the images, to crop them, and to stack together to get like the proper stereo 180 image. So those lenses allow us to extend the field of view. So on the left, you can see the old field of view with old lenses, and on the right, the new field of view. One more issue that you have with cameras and stereo vision, is that you want to have image for the left and right eye aligned together. And so not to make it manually, we did the calibration script, which uses OpenCV, which uses the checkerboard, which you can see on the video, which you can just move around the cameras, and the camera and the OpenCV function, the script, would find the optical sensor, and then you can perfectly align it together.
All right. Regarding the remote connection, we have two setups. So basically, one is the setup was setup, and the other one is the WebRTC setup. We decided to go for WebRTC, which is a technology usually used for video calling on the web, because it allows us to have remote connections from anywhere in the world without having to set up a VPN or anything. And WebRTC brings a lot of these default, like things that are usually hard to do, like encryption. It brings tunneling through all the firewalls in between, and it allows us to transmit video, audio, and data channels. WebRTC, we are using the AIO-RTC library for Python. And it is connected, it's running on the robot, it's connected to all the robot modalities, vision, audio, and such. And you can connect from any outside computer to it. Additionally, we have a signaling and stun turn server running on a server in the cloud, which basically allows us to connect. The way WebRTC works is WebRTC is a peer-to-peer connection. So the data goes directly from one client to the other. But in the beginning, they have to basically once exchange their addresses so that they know where to reach each other. For this, in the beginning, you need the middle server, which is basically running on the cloud. We have working connection for audio, stereo audio in both directions. So you can hear what Roboy hears. And when you say something, Roboy plays it back. And we have the head motion, which is basically, like you said, the head location for the delay compensation. And we have joint control, so robot can be controlled by the operator. For the video transmission, we're able to have detailed control over the bandwidth, the resolution, and the frames per second that we transmit, which we want to use to give the best possible quality to the operator. Although we haven't fully achieved writing a controller for this in the semester. Yes.
All right. So I would like to give a little info about the operator side of the things. So this is how our operator communication stack looks like. Which one is it's not working. It's not working. Which one? Top one. No, the bottom, I think.
I think battery is low.
It's okay. So we have a server base and 3 classes inherit from it. Previously we were connecting via a new server. Now we have WebRTC and a server, and also we have a mock server that we are doing our tests when the robot is not available. So RTC server and as well as Roboy server has these two main properties. They are responsible with sending from operator, like VR positions, our head positions, our control positions, from operator to robot, and there is also head positions and head subscriber, which is controlling the I-squares that we created in the unit side. Yes, and which allows us to do the motion compensation. So, as Susanna and Dan already mentioned, we are using fisheye cameras and we are receiving and sending the head positions. Consider this user story. We are looking at a straight point, and this is step one. And when we turn our head to right side, we are seeing the corner of this I-square, but we are still able to see some of the view thanks to the fisheye cameras. But it takes time to robots actually move this head to that position, and after that happens, the current, like the previous system, was getting this field of view to the center. So we were at one point looking at the computer, but the center is changed after. With our implementation, now I-square also is moving with our movements, and By the time robots had moved to that site, our field of view center stays in the same. At least this was the hypothesis. But in real world, in our application, we saw that there is some problems with it. So as you can see from the right bottom, there is a little flickering rate. So robot tries to make the field of view center, but it seems flicker. And the reason why is that current implementation requires us to separate videos and the data about the head positions. If they were to sync and have the exact same time frame, so for a video frame, we have the robot positions exactly. This wouldn't result in this flickering behavior, but we will have a proper motion compensation. So for the possible solution in the future, as Furkan Kaynar, who is advised us about this motion compensation, he suggests that we can embed this joint information to videos, and this way we will not have this issue of flickering. So, at the what we have achieved is that we have fisheye cameras and stereo microphones installed in Roboy. We have a WebRTC in Roboy. We have a WebRTC signaling serving as well, which is not currently working, but we are able to locally connect the robots. Some high performance issues about the FPS we have already, but we are getting somewhat good videos. So operator rework where we refactor a lot of things in projects by Susanna is done as well, and ROS network update is done as well. Robot control, we have hands moving, hand moving, but not wheels. Motion delay compensation is not simple video, it's the problem that I just described, and phase switch energy that we don't have. So, challenges.
There were a couple of challenges that we encountered on the way. WebRTC is surprisingly high. So even though WebRTC sounds like this very similar technology that basically everybody's using, you might think it's basically a solved problem. There are libraries, you can use them. It isn't. There are bugs in the libraries. In the meantime, we had to fix bugs in the libraries ourselves and provide pull requests. We have issues with the video encoding performance sometimes, depending on which hardware we use on the system. Especially since the way that we access the camera requires a certain method. So while in our test system, which was less performant, we achieved almost 30 FPS in full HD, we are not achieving that anymore on this robot right now with the current system using OpenCV. Also because there's a lot of other stuff running on the robot itself, which basically competes for the CPU. For example, the Python GIL. If anybody knows what this is, they will be as unhappy. We did a bit of validation to figure out what latency we can achieve, because this is a key metric to us. Using the web implementation, basically use the web browser to view the video. We are able to achieve 0.3 seconds, so 300 milliseconds latency for audio and video. In Unity client,
on the same network?
We did not see that much differences in the network. So basically, most of these latencies are buffer latencies on the receiving side and the sending side. So on the Unity client, it's a bit more. Typically, you sometimes get better performance, sometimes a bit worse, but 1 second is what we usually achieve. No, it depends.
I mean, 1 second there.
Yes, yes.
But there is also the data channels that's being
Yes, the
in the
interesting part of the
picture.
data channels, you see that the data is there immediately with the video channels. There's some buffer in the Unity implementation of WebRTC that buffers the video and only plays it back like after some time, and this is basically the issue you're fixing. And because it's a Unity provided implementation, it's really hard to dig into the details and try to rip out whatever causes the latency. Yes. And we would like to demo everything. If it works, it should already be connected. So let's try to switch to the web page and see if this live stream is running. It is not. Huh?
Restart the
I'm
web
gonna
page.
try to start it again. The headset turned off. Yeah, I need to restart everything.
Looks like the head is still trying.
A second. Can I get the?
Daniel head is of the Roboy is turning.
Yeah, let me check.
Are you in the correct live?
I still get live video, so that's good.
That's a good
Yes.
question.
Yeah, no.
No.
You should be able to see our live video coverage. And what you can see here is the motion compensation,
How do you see it?
where basically I move the view to the left, and you see the view also moving to the left. After some time, the robot moves the view to the left, and the latency compensation compensates the robot moving, so the video stays centered.
Yes, this flickering behavior is the thing that you look at, I think.
What feedback are you using now? The simulation or the joints?
Simulation. So it could be better even. Yep.
Yes. So it should work that if I talk here, you can hear me from the robot.
Yeah, it works. Yep.
One effect you see right now is that the color is a bit off. This is because we removed the infrared filters with the new 180-degree field of view lenses, and that kind of breaks the white balance, unfortunately. If anyone wants to try it out, you can go ahead. Any questions?
Any question? We have 2 minutes. Yep.
And I can control VR.
Yep.
Are you sure this is really just like the filtering is really just frame time sample line?
Yes.
And not the controller issue? It's
Both.
Basically, you're jumping. I mean, I would expect this to happen because
I fixed this right now by just adding a 300 millisecond delay to sending the motion data. And now it's basically way better than it was before.
Yeah, but still like the head orientation we are getting from the simulation and not from the sensor inside the neck.
Yeah.
So it's not like accurate enough.
The issue is that in Unity, you can get no information about what is the timestamp of the frame that is currently displayed.
Yes, whatever comes goes to the iSphere, so and we don't have any manipulation of the frames possible. We tried it in the midterms, until the midterms. We tried to do our own encoders of the frames, but it introduces such a long complexities, like space complexities, I think, and we were not able to do it properly, like a video call.
But right now you're also like moving the picture immediately, right? So you jump, the picture jumps. So if you move this a bit, you try.
So whatever comes from the position of the head goes to the iSphere. So
Yeah, I understand. I was just thinking it's like right now, what happens is it comes a bit corrected, it jumps too far, then it moves a bit, and it comes back, and then it's a bit like switching behavior. But if you would just low pass filter the motion on the ice there, it might just actually filter.
Right now you see it desynced quite a lot. Like if I move, you see the image moves and then the image moves back.
Yeah. But what I'm saying is like right now you get this relatively high frequency jitter. And then if you low pass filter the motion of it, it might actually like perceptually be a lot better than this kind of.
That's like something that you need to test to get the feeling if it's better or not. Okay.
So this was us. Thank you very much for this.
So maybe another question, like what is the main reason that we don't have 13 FPS? When is it working higher, faster?
Different video encoding stack.
So basically the problem is that the encoding is already too slow.
Yes, we cannot send more than 10 FPS right now. It's a weird, like it's not all of it is CPU problems. It's weird issues where different parts of the software are blocking each other. And yes, and OpenCV is not the best for this kind of like very live processing. So we tried to move it to the hardware because like this is an NVIDIA Jetson Nano. So I spent a couple of nights last week trying to move it to the video encoding hardware. But that turned out even harder to do and to get right. But obviously that was our kind of our end goal, to really use that hardware, because we wanted to achieve 4K video resolution, which you don't have right now, but you saw a 720p. Yeah. In the web browser, it works better with 1080, but 4K was our goal, but that requires hardware encoding and the hardware pipeline to run.
Okay, thank you.
Okay, wait, don't run away. I have a special thing. I've never done this before, but this semester was a remarkable, phenomena. Like I was really impressed how much time Susanna spent on refactoring. And I got, so the best stuff is inside, so I got a little present for this. So this pain is like, I feel it and it's really good and it's super clean now. So
very cool.
Okay. Welcome. Here from the team of Roboy and this year. Bonnie is today not here, sadly, but I will try to do his part two. Our goal was to make Roboy more capable to work in a clinical environment, or that is at least the final goal. And we tried to find some ways to go to the goal. And for this, Roboy needs some skin over the arms. that it can be used there, because with all the open parts we can't provide some disinfection, and therefore we need some skin that goes over the arm that's completely closed, so we have an easy surface to disinfect it, and then it's usable. But right now with all the open parts it's not usable, and that's one problem that we tried to tackle. And also you see the orange parts on the hand of Roboy. These are some TPU parts, and they are not perfect to grip some things. So we tried to develop some skin also that is more capable of gripping like a normal human hand, while still keeping the hand flexible enough that it moves. And also we wanted to improve the wrist, because the current wrist is not working anymore, and it has some disadvantages. And for this we designed a new wrist mechanism and tried it out a little bit on what it can achieve. Boning is not here today. He had most of the part to do with the skin, but I have some pictures from him. On the left part you see the orange things that we molded again with silicon, and on the right we have the mold where that we used for it. Until now we had often a problem. We have mold, and we have another part on top of the mold, and in there you see some lines, and through the lines the silicon flows into the forms, and in there it gets hardened out, so that you have the pieces on the left picture. But normally when you put some pre-printed parts together, they are not tight completely, so the silicon will flow out. That's a big problem, but we can't just make one piece in mold, because then we can't get it out, or we have to destroy the mold, and then we don't want to. So we had the idea that we use some knete that we roll out and put around the lines where the silicon has to flow, so that we can press it together. The silicon can't flow out anymore. And with this, we got some better results than the years before. And also, Boning tried to find some gloves, because the plan is that we have the orange parts made new, and these parts we wanted to glue inside a glove. And for this, we got different glove types and tested them how flexible they are and how long they can hold. So yeah, there are some funny tests there, and tested all of them over 10,000 times, if they hold or if they will break at some parts, because if we get some leaks in the skin, that's not good, because then we have to make it completely new. And if it's too often, then it's not capable for any high demanding use case. Yeah, and on the right part, he tried to put some silicone by hand over a finger to create a skin completely by our own and not using a glove. But as you can see, it's really rough, and we are trying to find another way, like just dipping the finger into the silicon, that we have just a small film around it. Because the problem is the skin has to stay tight on the bone, and it has to be fixed there. Because if you try to move it around, your skin won't move much along the bone. It's pretty much fixed there. But in the joints, you have to stay flexible, because otherwise you block the joints, and then Roboy's hand can't move that good anymore. Yeah, and these were some challenges that Boning tried this year, and we made some achievement, but we didn't make a whole skin glove for the whole hand and arm. And also he experimented with adding some heating wire for the into the hand, that you can heat up the whole skin to human temperature, because then when nobody touches you, it feels more normal than if you have just some cold plastic thing that's touched you. And in clinic environments, it would be much better if nobody feels more natural to you. And for this, we just have a heating wire inside the skin that we kept around the temperature of the human body. And this worked relatively good, but at a high power consumption. But in the future, when we have a whole skin over the arm, we could use some of the waste heat of motors that are also in the arm to support the heating mechanism, so that it gets more effective. The old design of the wrist. The old design of the wrist was that we have a ball joint in the center and some tendons that move it around. So we have a big surface area of the ball and the form where the ball sits in, and this creates some friction. And we have two motors that act against each other. So we have sometimes the problem that they start to oscillate, and then we can't move that precise anymore. And these are some of the problems that we try to tackle. And for this, we first researched what other kinds of mechanisms there are. For example, there's a really easy one. It's just serial link. That's the smaller picture in the background. You have just one joint per axis, and then you have some straight part to place a motor in there, or to provide some distance, because we can't put them all in one place. Then they can block each other. And this is really easy, but has some problems. For example, we have in every direction some offset. So if you want to move in this direction with your hand, then you have one offset from the joint to the hand. And if you move to another section, then you have another offset to the next, to the moving part. And depending how many dimensions you want to rotate, this offsets add up or reduce. So every movement has another offset, and that's not so easy to control, and it might not be that convenient. Another approach would be that we use some hexapod. That's the 3D thing with the pistons there. The problem is it has, the good thing is it has 60 degrees of freedom, so it can completely do what a wrist can do. But we need some linear motors in there, and more motors than we need. Or we have to add some pneumatic or hydraulic system to our body, and we don't want to do this. And we wanted to stick with electric motors, so this is also not what's used there. There are also many different versions of other joints, but they often have the problem that they are really complex, and we are not sure if they are strong enough to handle the loads that we want to add there. So we selected and so we wanted to use some spherical parallel mechanism. It's spherical because you can see up there are these silver shiny points, and these points are always on one sphere and moving around. And these are arms that move the big plate in front around. And this approach was taken into account for a paper where they built a rescue robot, and the rescue robot used this for its manipulator, and they wanted to do some heavy duty stuff with this. So we were sure that this mechanism can definitely do more load than we need. And then the main goal for us was to shrink it down so that it fits in our joint hand, in our wrist, and not big like for the rescue robot also. And this has the advantage that we have some universal point where all other axes rotate around. So we have one fixed offset from the rotating point to the hand, and there is no change in between different movements. We had some challenges with it because it's a funny mechanism, but it's hard to calculate all the forces because in all different joint points we have some force. And you have to calculate it beforehand that we know how strong the parts have to be. For this, the paper had a section that explained how to calculate the forces at different points. And then I wrote a small NumPy script that calculates us. We can just say our plate should move this force, and we moved it around through the whole area of movement that we want to achieve. And then we selected the highest force vectors for the different points. And then we had known the maximum forces that our wrist has to take. And then we could design the parts that they are strong enough. And the other challenge was that we have to reduce the size. And as soon as we reduce one part, we have to also change all the other parts. So it's a relatively complicated approach because one part's changing, everything is changing, and then everything starts from around, and some parts collide sometimes together, and then we can use a lot of time to find a good solution. Yeah, and here is our prototype of it.
We have not just the wrist. The wrist is just the front part here. The rest is the lower arm. This part here will be mounted in the elbow, and then it can rotate. And these two motors on the side, they can control or plate in front of it, where the hand is mounted. And then the motors have some tendons that rotate the wheels, and depending how these two wheels rotate to each other, these arms here will move the plate to different positions. We planned to do some demonstration of it, but the problem was that the microcontroller signaled us with magic smoke that it doesn't want to do it anymore. So sadly, the practical part has to be done another day. Yeah, and my time is up. Yeah, me too. Yeah, do you have any questions?
What do you see as the weakest part of this design?
The plastic parts. We calculated it with the nylon of a Roboy. With the nylon, we had a plan that we can move a cup of water with the hand. So we estimate a weight of 1.5 kilograms to move. And we designed all the plastic parts to be out of nylon. And the nylon parts, they should be able to keep the forces. But I don't can print nylon at home, so I use just PLA, and it's much weaker. So probably it won't make it as good as we plan to. But with professionally manufactured part, it should be capable of it. But I think especially the wheels probably they are the first part that will break, because they're really small and they have to take most of the forces. And you all made some metal sheets for me that they are more stiff and take more loads. But at the beginning, we planned to do them completely out of plastic, and then it probably wouldn't be sufficient. We can also come and try and test it.
Yes, it will be there. All of the demos are still active after.
So, how robust is it against impact? Is it dark variable or like with arms? They break?
Our arms are completely made out of metal, so they won't break, or at least the plastic parts will break much more earlier. Some of the forces can be taken by the arms because they can wiggle a little bit. And then also we have the tendon drive, and the tendon drive can keep also some impact. So we have some impact protection.
The tendons are so most of them are about mechanism.
It's big variable. I can move it around, and if I do it hard enough, then the motor is rotated with it. Yeah, but the problem is you have to be precise with the radius of the sphere, because all the parts have to lay exactly on the radius, or at least the joint, the rotation parts. And otherwise, we have some problems currently that in front of here the nut is colliding with the wheel. So currently we can't move the hand like this. But if we fix this part and make the radius correct again, then we can move over it.
So pizza is also here. Thank you so much. Now it's time to test the demos for others and enjoy pizza and some nice conversations.
Good job. Ich denke schon, oder?
You know how to, sorry?
Sorry, do you know how to?
I don't know. What
Dude, like I have no idea about the mechanics, but I love, like the seeing these designs because they're incredibly small details that you have to care about, like those small calculations. Probably for the engineers, it's the most frustrating part, but it seems quite cool. Like I was just telling him, like if I was not a like a programmer, if I didn't study CS, I would definitely code mechanics.
What were you studying?
I'm studying CS. My university. I mean, usually I mean, of course, like I'm not talking about everyone, but if someone is studying CS, that person is really bad at hardware. Yeah, I have really. Yeah, the same. Yeah, me too. Like, I'm also shit at hardware, but I mean,
Then
these
also,
things.
then also studies informatics.
Hardware. Some guys love it.
Maybe you also.
I didn't. Okay, dann drücken wir kurz raus.
Geil.
Lunch go? Did you have a question for aber nicht ganz mehr. Das hier ist halt ein ganz cooles Experiment, man kann es einfach so bauen und dann gucken. Never ending. Ja,